Moving on, we will discuss about the concept of polarity. For covalent compounds, we recognize two different molecules. We have the polar molecules and we have the non-polar molecules. In the chapter 1, I have introduced to you the concept of electronegativity. You can revisit this concept again in chapter 1. The point is, if you have no difference in electronegativity, for instance like FF or oxygen, like that, or other things, nitrogen, N2 and Cl2, and so on and so forth, or hydrogen, we have no difference in the electronegativity between the two atoms because they are of the same atom. Therefore, in this case, we have the non-polar compound. This is different when we have something like HCl, or if we have something similar to HCl like HF, HBr, and so on. Because we have a significant difference between the electronegativity, Cl being more electronegative than H, the electron that is being shared together in the middle actually will be pulled closer toward the Cl, making Cl a partially negative pole and H will be a partially positive pole. In this case, we have a polar compound. Now, in a more complex structure where we have more than two atoms, we can understand the concept of polarity based on the shape of the molecules. In general, when we have a symmetrical molecule, symmetrical arrangement usually result in a non-polar compounds. However, we have to be really careful in which molecules are symmetrical and which are not. Let's take two molecules as an example. Suppose we have CO2 and H2O. If we to write down the Lewis structures of these compounds, you will write down CO like this and O surrounded by hydrogen like that. Now from here, it is very easy to make a wrong guess. It seems that both of these molecules are symmetrical. Would you agree? The answer is actually no. Not all of them are symmetrical. To understand this, we have to visit the concept of shape of the molecules. Now, for CO2, we call this structure as a two-domain structure. Each of the bonding pair and the lone pair, we count them as one domain. So for CO2, we have the first domain and the second domain. So it is a two-domain structure. It doesn't have any lone pairs, so the structure itself will have a linear shape. And indeed, due to the linear shape here, we have a perfectly symmetrical compound. Therefore, CO2 is indeed non-polar. However, this is different with the case of H2O. H2O is actually not a two-domain compound. It is rather a four-domain compound because we have 1 and 2 and also 3 here and 4. So we calculate each the lone pair as one domain. So it's actually a four-domain. Meaning that structurally it's not comparable to CO2. It is more comparable to other component or other compound, which is CH4 N, and H3. In principle, H2O is more comparable to methane or CH4 and NH3 or the ammonia. And in this case, we can start from the methane over here that has 4-domain. So actually, the structure for 4-domain system like this, we call it a tetrahedral structure. So it looks something like this. You have 2 that is on the plane, and 1 will go up towards our side that we normally draw like this, and 1 will go toward the back of this board. So if you imagine this is a plane, 2-dimensional plane, this and this will be on the plane. This will come from this point towards you, and the other one will comes from the plane towards the back of this board. This is what we call the tetrahedral arrangement. However, because CH4 has 4 hydrogens surrounding one C, this particular structure is also a non-polar structure because it still has the component of symmetry due to same 4 hydrogens surrounding 1 carbon. Now, with the same tetrahedral structure, we can start substituting the H atom with lone pair, in this case of ammonia, and 2 lone pairs in the case of H2O. Let's draw them. So for ammonia, what we have is N, and then H, and then another H going back towards the back of this plane, and another one will be still on the plane, and the other one will be non-existent because what we have is a lone pair. However, for oxygen, we have even more lone pairs. So this will be H, and then this one is also H, and this will be a lone pair, and that will also be the lone pair. So we have 2 lone pairs. That makes the geometry of both ammonia and water will be different. It is not longer tetrahedral, but now for the water, we call this phi-shaped because it looks like a letter V. Okay? While for the ammonia, we call this a triangular pyramid. Because if you take a look from the bottom up, it looks something like this. We have N, H, H, and on the back H. So it looks something like a pyramid, but is formed by a triangle. So in this case, we can see that the H2O structure is actually not symmetrical. It is rather V-shaped. Therefore, this non-symmetrical structure will result in the water being polar molecule. Similarly, for ammonia, it is also not symmetrical. It's not a triangle, but rather it has a structure of pyramid, but has a triangle base. So ammonia is also non-symmetrical, and therefore ammonia is also polar molecule. While we're at this, we will also discuss the angle between the 3 different atoms that we can see in here. For instance, in the CO2 structure, the angle between one CO with the other CO would be the same, which is around 180 degrees because it's a linear structure. For tetrahedral, we actually have C and H only. And in this case, the angle for tetrahedral structure is around 109.5 degrees. However, the lone pair actually will cause more repulsion. For instance, in the case of ammonia, this angle will be even closer, so it is 107-ish degree. And for water, because it has even more lone pairs, the angle will become even lower to around 104.5 degree. In general, the lone pair repulses the most. This is known as the theory of VSEPR, or valence shell electron pair repulsion, where in general the lone pairs, they repulse more and therefore they cause the angle to become even smaller for the one with more lone pairs.